I'm Nuozhou, and this work is with Liyan Chen over there and Zhihao Tang over there. And let me first introduce our set in online selection. In online selection, there are n boxes, and each box is associated with the value distribution. Yeah. Here, the figure is an example where n equals to 3, and the value distribution is as shown on the figure. And each time a box will arise, and the agent will see the value inside the box, and they should immediately decide either to choose the box and leave, or discard the box and wait. If the agent choose the box, then it will get the reward inside the box, same as the value inside the box. And it will no longer see the rest boxes. And if the agent choose to discard the box, and when the next box arrives, it can no longer pick the first box. And the objective of the agent is to maximize the value it can obtain in expectation. And here are some type of knowledge, the type of algorithms we will consider. They are classified by the knowledge owned by the algorithm. The first one is offline algorithm, which knows the exact value inside each box. So it's like making decision offline. And the second algorithm is called online algorithm, which only knows the value distribution of the boxes, but not the exact value inside box. So this type of algorithm will know the exact value only when the box arrives. And now if we compare the online algorithm with the optimal offline algorithm, then this is something called well known as profit inequality. And there are already a lot of researches on this, especially in the EC community, because this is equivalent to the sequential positive pricing. And there are raising interest in comparing with the optimal online algorithm instead of optimal offline algorithm. And this is also our setting. In our setting, we further separate the online algorithm into two categories. The first one is called order unaware online algorithm, which only knows a collection of distributions, but not the arrival order. So in its view, it does not know what box will come next. It will only knows what box is when it arrives. And the second type is called order aware online algorithm, which knows the arrival order of boxes and the value distribution of each box. So this is generally the general definition of online algorithm. And the ratio we analyze is a ratio called order competitive ratio. In this ratio, we consider the worst case over possible value distributions and the arrival orders of the ratio between the expected value obtained by order unaware algorithm and the expected value obtained by the optimal order aware algorithm. We know that the optimal offline algorithm will just pick the maximum value because it knows the exact value of all boxes. And let me give you some insights about how the optimal online algorithm works. Generally, it will pick the box if and only if its value is greater than the expected future reward. And the future reward can be computed by backward induction, and the formula, we'll discuss the formula later. Here, let me give you an example to help you better understand the order competitive ratio. Here are three boxes, and the value distribution are shown on the figure. And now suppose the box 1 comes first. And let's discuss how a deterministic order unaware algorithm will act in this scenario. Because it does not know whether the box 2 or the box 3 will come next, so it must consider the two possible arrival orders remained. The first possible order is that box 2 comes next, and then box 3. In this order, the optimal algorithm can get expected value nearly 2 by not picking the first box, because it can pick the second box if the value inside it is 100, and otherwise pick the third box. And if our order unaware algorithm picks the first box, then its ratio is at most square root 2 over 2. Okay, let's see the second possible order. In this order, box 3 comes next, and then box 2. In this order, the optimal algorithm can get at most square root 2. But if the other unaware algorithm does not pick the first box, then the ratio is still bounded by square root 2 over 2. So in summary, if our algorithm picks the first box, the ratio is bounded by square root 2 over 2 in the first arrival order. And if it does not pick the first box, the ratio is again bounded by square root 2 over 2 in the second arrival order. So this example basically shows that the order competitive ratio of a deterministic algorithm cannot be square root 2 over 2. Okay, and let's talk about some results in this setting. EC'24 et al. Showed that a deterministic algorithm can achieve the golden ratio as the order competitive ratio, and the ratio is tight. And the natural question is that can randomized algorithm achieve better order competitive ratio? And we answer this question by showing that there is a randomized algorithm achieves 0.732 order competitive ratio. And now let me introduce how we design this algorithm. Basically, the idea is first design a deterministic algorithm and add randomness to it. But it's not straightforward. So the start point is to record the behavior of the optimal online algorithm. Remind that it will pick the box if and only if its value is greater than the expected future reward. And the future reward can be computed by this formula. Here, the opt-I is the expected rewards obtained by the optimal algorithm if it starts from the icebox in a fixed arrival order. And BI is the exact value inside icebox. BI is the value distribution of icebox. And this formula basically says that the optimal algorithm will pick the maximum between the exact value and the expected future reward. And this backward induction shows that if we have opt-I plus 1 and BI, then we can compute opt-I. And an important observation is that this formula is inversible, which means if we have opt-I and BI, it's possible for us to compute opt-I plus 1. And this observation enables us to design an algorithm in this way. Suppose our algorithm knows opt ahead of arrivals. Here opt is the expected rewards gained by the optimal online algorithm. Then our algorithm can do the following things. Basically, on arrival order of box I, it can first compute opt-I plus 1 from opt-I and BI. We can do this because we have the formula to compute this. And then we will choose the box and leave if and only if the exact value inside the box is greater than opt-I plus 1. And we claim that this algorithm achieves the reward same as the optimal, the expected reward achieved by the optimal algorithm. And this is because this algorithm behaves completely the same as the optimal algorithm. And the above algorithm just showing that if we know the optimal ahead of arrivals, then we can design an algorithm that achieves the reward same as the optimal algorithm. But the problem is how can we learn opt ahead of arrivals? Basically, it's impossible for us to do this because otherwise we get an algorithm with order competitive ratio of 1. But we can have a guess. So now it's time to describe our algorithms. Our algorithm named as targeted value algorithm is parameterized by a targeted value G0. And our algorithm claims it wants to collect an expected reward of G0. And G0 is the guess target. At the arrival of box I, the algorithm will do the following things. First, it will compute Gi, which is the minimum number that if we can collect an expected reward of Gi from the future, then we can achieve G0 generally in expectation. Here Gi is similar to opt-I plus 1 in previous slides. And our algorithm will pick the box and leave if and only if the value inside the box is at less Gi. Here is an example to illustrate how our algorithm works. Suppose our algorithm is parameterized by G0 equals to 3. And this is an array order. First, when the first box comes, our algorithm will compute G1 equals to 2. Because with high probability, we can get reward of 4 from the first box. And if we can get expected reward of 2 in the future, then in expectation, we can get G0, which is 3. And if the value is 1 in the first box, because V1 is less than G1, we will not pick the first box. And similarly, we'll compute that G2 equals to 1, because with half probability, we can get 3 from the second box. And if we can get 1 from the future in expectation, then we can collect reward of 2 from the second box. And because G1 equals to 2, which means it's able for us to achieve G0. And if the value inside the second box is 3, then we will pick this box and leave. Also, we will compute that G3 equals to 0, which means we don't need additional reward to achieve G0. And because in this concrete example, because we already picked the second box, we will no longer make decisions here. And there are some claims about our algorithms to prove the order competitive ratio. The first claim is about the underestimate case. It says that for an arrival order, if the optimal algorithm can achieve more than G0, then our algorithm can also achieve more than G0. And the second lemma is about the overestimate case, which says that for an arrival order, if the optimal algorithm cannot achieve G0, then we can at least achieve the expected maximum minus G0. And note that with these two lemmas, it's able to get a deterministic algorithm which achieves the golden ratio as the order competitive ratio. This is done by set G0 to be the golden ratio times the expected maximum. And knowing that this ratio is tight, proven by previous works. And this is the byproduct of our project. And let me give you some intuition about why these two lemmas are correct. The first is about underestimate case. Recall that GI is the minimal number that if we can collect an expected reward of GI from future, then we can achieve G0 in expectation. This definition basically implies that GI is monotonous on G0. So if our algorithm can succeed with G0 equals to optimal, then it should also succeed with smaller G0. Here, succeed means Gn equals to 0 in the end, because it means we no longer need additional reward to achieve G0. And this is why the lemma holds. Also, for the overestimate case, we can prove that in this case, our algorithm is always better than a single threshold algorithm with threshold G0. And this is because in overestimate case, G0 is too high as a threshold. And what our algorithm will do is gradually lower the threshold. But the single threshold algorithm will never lower the threshold, so it will do worse than us. And with typical techniques, we can show that a single threshold algorithm with threshold G0 can obtain at least expected maximum minus G0 in expectation. And this is why the lemma holds. And the last step is add randomness into our algorithm. Basically, G0 is the value we want to guess, so we can sample it from some distribution. And we show that if we sample G0 from the distribution shown on the figure, then we can achieve order competitive ratio of at least 0.656. Here in the figure, we assume the expected maximum is 1. And also, we have some improvements to our algorithm. These improvements get a better row bound in the overestimate case. This algorithm named targeted value algorithm with detection, if this algorithm discovers that the optimal algorithm cannot obtain G0 in expectation in this arrival order, which means even the rest boxes comes from the optimal order, we still cannot obtain G0. Then we will give up the original algorithm and start a single threshold algorithm to get at least half of the expected maximum of rest boxes. And this single threshold algorithm is guaranteed by the profit inequality. And we can show that this algorithm, in the overestimate case, this algorithm can achieve the maximum between G0 divided by 2 and expected maximum minus G0, which is a better row bound because the previous row bound only has a first term. And if we sample G0 from the distribution as shown in the figure, then we can achieve order competitive ratio of at least 0.732. And this is how our mean result comes. Also, to complement our paper, we give some hardness results. First, we show that no randomized order unaware algorithm can achieve an order competitive ratio better than 0.8293. And this is obtained by analysis of specific type of instances that all but one boxes have fixed values. And note that this type of instances is in some sense strong because it's enough to construct the worst case for deterministic algorithms. And also we show that our design algorithm is at most 0.7582 order competitive. And this is all of our results, and thanks for listening.